I welcome you all to the Spark Research YouTube channel. This is Dr. Vision, the Assistant Professor in the Department of ECE. And in this session, we are going to take the contents from this signal processing. And currently, we are running in the unit second, and this is the last session of this unit second. Here we are going to take the contents related to the analysis of the continuous time signals and system. Before going ahead, let me tell you about the upcoming sessions. First of all, we'll cover all the 5 minutes from this particular signal processing course, and also we'll take the questions from the past years and followed by the gate related questions from this particular course, that is signal processing, which has been asked in the previous years, right? Okay, so here is the syllabus for your unit second, and in this session we are going to talk about the particularly the Laplace transform, inverse transform, and then ROC, and then we'll see the analysis of LTI-CT system also, right? And problem based on that. So let's start. So first question is that what do you mean by this Laplace transform? So if you remember in our previous session, we discussed about the Fourier transform. So Laplace transform and Fourier transform is much more similar to each other. However, here if you will see the differences that instead of the j omega t, we are using s minus of st, right? So s is nothing, s is equal to j of omega only, but in Laplace transform, we are converting into the s domain, right? So s is also the complex frequency only, but the s domain is a special term, right? Here, and also integration, if you'll see here, we are integrating over the 0 to infinity. For representation, like suppose this is the exponential function, actually here it should be exponential function y of t is equal to suppose e to the power minus t. Then if you wanted to convert into the s domain, that is the Laplace transform, you can put it here like y of t is equal to this, then replace your y of 2 to like e to the power minus 2t and multiply by this e to the power minus st, and then integrate it over minus 0 to infinity in with respect to the dt. You will get the y of s, that is 1 over s plus 2, right? So this is in the Laplace domain and this is in the time domain, right? So the major objective of Laplace transform is again convert from time domain to s domain. Clear? So let's see the examples here. So Laplace transform, first of all, we can use this equation only in order to convert into the S domain, multiply by e to the power minus st and integrate it over 0 to infinity with respect to dt. Ft is your function. So whatever the type of the functions you wanted to convert into the S domain, just replace this ft by that particular signal. As for example, let's take the Laplace transform of 1. So here f of t, we can replace f of t by 1. So 1 into e to the power minus st dt, and then integration from 0 to infinity. That's all. Now you can integrate. So exponential function integration is e to the power minus st integration equal to e to the power minus st divided by minus of s, right? And now you have to put the limit, that is 0 to infinity. Now put the limit. So e to the power minus st divided by minus s. So if we put 0, so it will be 0 and minus and e to the power minus st. So here if you put, you will get 1 by minus of s. So s is equal t is equal to infinity, then e to the power minus st will be equal to the 0, right? So e to the power minus st means e to the power 0 equal to 1. So 1 divided by 1 over minus s. So finally, your answer is 1 by s for Laplace transform of 1, right? So what we did here, we simply replace the f of t by that 1, right? Similarly, we can get the Laplace transform of any function as well by using this integration technique only, nothing else, right? Okay, so one more example, Laplace transform of exponential function e to the power at. Now we are going to replace f of t by e to the power at. So now you can integrate it over 0 to infinity, multiply and integrate it. Here these are the steps you can see, and once you will integrate, you will get the answer 1 over s minus a. So exponential function, same integration, e to the power minus st is equal to e to the power s divided by s. So as here this term will be a minus s, right? So you will get this value. Here is the summary of the basic Laplace transform. So Laplace transform of 1 is already we got 1 over s. exponential we got 1 over s minus a, and similarly if you will get the Laplace transform of t, you will get 1 over s square sine bt cos bt. You can get like this type of the Laplace transform. So you should try to do these Laplace transform. You can convert the sine and the cosine function into the exponential using the Euler's theorem, and then you can get the Laplace transform, right? So now let's talk about the inverse Laplace transform. So inverse Laplace transform is the process of finding a function ft given its Laplace transform fs. So it is denoted as L inverse f of s is equal to f of t, right? So we again converting back into the time domain, that is called inverse Laplace transform. As usual, like inverse Fourier transform, right? So we can do either using the standard transform pairs, means if we know, otherwise we can do the partial fraction decomposition technique. So here is the example. How can we take the the how can we convert back, that is into the inverse Laplace transform using the partial fraction technique. So suppose this is in the S domain, 2 divided by s into s plus 3, and we want to convert into the time domain. So how can we do? First use this partial fraction, so we can rewrite the same equation is equal to a divided by s plus b divided by s plus 3, right? So a something a divided by this, and you can see just this we want to write this function in terms of this. Now you can the equate the left side and right side and get the value of a and b. So once you will get the value of a and b here, then finally we'll have 2 by 3 divided by s and 2 by 3 divided by s plus 3, right? So if you remember, then u of t have the Laplace transform of 1 by s. So this is something like that, right? So here we can write 2 by 3 into 1, and then if you remember 1 over s by, the s plus 1 have the Laplace transform something like e to the power minus at. So here 2 by 3 and then e to the power minus of 3 into t. A we can replace by 3. So this is the final answer of this function. So f of s is this, and f of t is 2 over 3 minus 2 by 3 into the power minus 3t. So this is the technique to get the inverse Laplace transform, right, using the partial fraction technique. Similarly, these are the common pairs here. So these are in the S domain, and these are in the time domain, right? So both are inversely, the vice versa. Means if you are converting inverse transform 1 by s, then it will be 1, and 1 by s minus a, that is e to the power minus a. And similarly, if you are converting back like the Laplace transform of cos function will be s divided by s square plus b square, and the Laplace transform of this function will be this, and the inverse of this will be this. So both are the related to each other, right? Okay, so now we will talk about the region of convergence. So the region of convergence of the Laplace transform is the set of the values of s for which the Laplace transform integral converges. So what are the possible values of s that will be the region of convergence? So the integral is valid in convergent only for certain values of s. It will not be valid for all. As for example, suppose we want to find the region of convergence for this e to the power at. So what will be the Fourier transform of this exponential? Of course, it will be 1 over s minus a. So now if you will check the values of s minus a greater than 0, so of course s must be greater than 1. So this is the region of convergence. So if s is less than a, in that case your the this s will not be valid, so this will not convergent. So ROC is s greater than a, then only your the s domain will be valid. This is the two-sided exponential, means e to the power the uh, the magnitude of your t here. So in this case it will be valid for the maybe the minus greater than a, less than a, and greater than minus a, right? ROC will be in this case. So you can write here e to the power at and e to the power minus at, and for e to the power at, the region of convergence ROC will be as greater than a, and for e to the power minus at, ROC will be the less than minus, right? So you can get. So ROC is always a right half plane or a strip in the S plane. So if ft is casual, then your ROC is form of the real part greater than the sigma, and if it is anti-casual, then ROC as is less than sigma, right? So ROC cannot contains the pole, must it not contains. Why is it not? Because at the S, the your the terms the domain will be infinity. So we must have to exclude it, because the denominator of your f of s will be 0, and if denominator of f of s will be 0, ultimately f of s will be infinity. So we must have to avoid it. Okay, so now let's talk about the analysis of the LTI-CT system. Laplace the linear time invariant continuous time system using the Laplace transform. So LTI continuous system is typically represented by the linear differential equation, here a n d to the power n yt divided by d to the power dt to the power n, and likewise. So this is the LTI system, any general LTI system. So taking the Laplace transform now, L of this left side and the right side. Okay, so that will give you the s to the power n y of s minus s to the power n minus 1 and y of 0, and then minus of s to the power n minus 2 and y dash 0. Y dash 0 is differentiation of y at value at t is equal to 0, similarly like this, right? So in this way you can get, and the transfer function is nothing, that is ys by xs. So left side is ys, and right from right side you will get the x of s. So basically y of s is in output side and x of s is the input side. So the ratio will give you the transfer function. So this is the transfer function in the by technique Laplace transform, right? So once we'll get the transfer function of any system, now it is very easy to get the output, because just you have to multiply in the s domain by the any input function, then you can get the output. So this is the technique. So let's see the some example. So here is the example of your first order system, right? First order LTI system. So here is a yt and xt. So first we can convert into the s domain. So dyt divided by dt. So differentiation, 1 times differentiation. So the s domain will be sys and y0 at the it will be given, otherwise you can put the value of t0 as s equal to 0, and you can get then 2 by 2, that is 2ys, and equal to x of s. From here you can get the value of the ys here, and so ys and divided by x of s, so that is a transfer function. So here you can get 1 over s plus 2 if y is equal to 0, right? Y0 is equal to 0. So this is the transfer function. Now if you want to get the step response, so simply step response means, so ut is your step function, and already you know the u of s is equal to 1 by s. So simply multiply, that is this transfer function into the unit step function, multiply and convert back into the time domain, you will get this function. So this is the step response of this first order system, for first order system using the Laplace transform. So what to do in order to get any response for any type of function? So step number 1, first we have to find the transfer function using the Laplace transform. Once and what is this transfer function? So ys divided by x of s means output divided by input in s domain. So once we will get the transfer function, then simply multiply by the input. So what is the input? Input is here step response. Step response means u of t. So input is 1 by s, so multiply and then convert into the time domain, that is inverse Laplace transform. That will be the final answer, right? Another example, here is the second order system. This is your system. Again we are going to find the value of y of s and x of h of s. So this is the transfer function of this system, second order system, right? And then for step response, again then multiply by the step, that is 1 by s. Now just we have to convert this into the time domain. So how can we convert? Using the partial fraction technique again, right? So if you remember in our previous to previous slide, we have saw that how to convert. So here we can rewrite the same equations like this value, get the value of a and b, and then convert it to the time domain. So this is the final answer of the step response of the second order system. Clear? So how to do step response of the second order system? So steps is that first convert this into the S domain, okay, and then get the value of the transfer function equal to the y of s divided by x of s. Once you will get the transfer function, then multiply by the input. So what is the input? Step response, that is 1 by s, multiply and then convert back into the time domain. That's all. So here is the properties. So linearity properties is there. So superimposition of the principle will follow. Time shifting, if you are shifting in the time domain, in the frequency domain it will be multiply e to the power minus ts. Frequency shifting, if you are the shifting in the frequency, that is s minus a, it will multiply in the time domain. Then differentiation, already we saw first derivative s of fs, second derivative, then s square fs, like third derivative s cube, like that. Integration, then fs by s. Convolution, convolution in time domain will be multiplication in frequency domain, right? So these are the major properties. So using the some linearity properties, you can check it here. So using the linearity properties, this principle will follow. So you can take the Laplace transform of this and this, and then you can add, right? So Laplace transform first component is already we got it, and for this also we can get it, and then finally you can add, right? So linearity property is holding, so multiply and then addition, right? So here it will be the final. Time shifting properties, like f of t is equal to t minus t, then u of t minus t. So in that case you have to multiply, right, in the frequency domain. So t of t minus t, u of t minus t. So t, it will be the results, that is multiply in the frequency domain by e to the power minus ts. So here t is 2 second, right? So 1 by s square for u of t, and so shift in the frequency domain, and so multiply e to the power minus 2 into s. So why is this e to the power minus 2 into s? Because here the t is equal to given 2, right? So t minus 2 is equal to 0, so 2, so multiply. So this is the final answer. So final answer of this Fourier f of t is there and f of s is here. How to get? Only one step, right? Because ut has the 1 over s, and t is actually t is there now, so t will be have the transfer function is 1 by s square, right? Okay, so here is the find the Laplace transform of ft. This one you can get. So this is the example, you can do it, right? So using the the properties, linearity properties, you can get it, right? Find the Laplace transform again. One more transform, you can check it. Just you can convert back into these differentiation properties you can use, and then you can follow the steps of the partial fraction, and you can get it, right? So that's all in this session. Thank you to join, and if you have any doubts, please drop your comments. Thank you.